So, today, Week 2, Class 1, what we're going to do is talk about situational awareness. And we need the Euler angles to get situational awareness. And do you remember how we defined the Euler angles from yesterday? We start from northeast down, rotate heading, out of the horizontal vector, rotate pitch, and then out of the I-axis of the aircraft, get your roll. So you can go to any attitude, heading, pitch, roll, or backwards. Roll, minus pitch, minus heading, go back to the LED. Pilot sees that when he looks out the window. How do you get that to him? Well, you have to give him the Euler angles and present them on a display in the cockpit. We'll show you those displays today. If you're using instrumentation, then inertial instrumentation, I should say. If you're not using simple aircraft instruments to get this, then you need to get the rates, roll rate, heading angle rate, pitch angle rate and heading angle rate. You need to get these rates, and then you integrate them. This triple roll, pitch, heading is not a vector. Do you remember why it's not a vector? Because the order is important, and in a vector order doesn't matter. We get it from integrating the rates. The rates are vectors. B dot's a vector out the nose of the aircraft. Theta dot's a vector out of that rotates about the J in the horizontal plane. And psi dot's a vector that rotates about the KV in the V system. So these are a vector. The order doesn't matter on these, but when you integrate it, it's not a vector. Unless, what? Was it? Anybody remember from week 1? Unless I put a little del in front of these, if these angles are small, less than 5 degrees, less than 3 degrees, then it becomes a vector again. We give this thing the symbol. If you look back at my 420 symbols chart, the symbol is the angular velocity of the B frame with respect to the V frame. That's the angular velocity. That's how you read this, the angular velocity of B with respect to V. And we're in the Euler coordinate frame, which is to be defined. We'll define that today. That little hat's important on the Euler coordinates. So the Euler rates come from the Euler coordinate frame, and they have this symbol. Now we get this either directly from the aircraft instrumentation, if it's a simple airplane, or we have to get it from inertial data. What do I mean by inertial data? Gyros, accelerometers, inertial navigation system, basically outputs will give you inertial data. That inertial data can be manipulated, and so we can say that our Euler rates are a function of the inertial rates. And the inertial rates have a different symbol. We have here an omega of B/I. And what that means is the angular velocity of the body with respect to inertial space. What you're seeing here is the angular velocity of the body with respect to E, with me, Earth, how fixed to Earth. If I was moving with it, then you'd see it with respect to V. The inertial instrumentation doesn't know anything about the Earth or moving. All it knows is that it's moving with respect to inertial space. Where's inertial space? Those Galilean frames that are out there floating between the galaxies. That's how God wants the universe. So we get instrumentation gives us output with respect to inertial space. If we mount the gyros on the body frame, if I mount one gyro on the I-axis, one gyro on the J-axis, and one gyro on the K-axis of the body frame, if I screw them down and mount them on there, then their outputs are going to be given by this symbol. The angular velocity of the body with respect to the inertial frame. Comma means BZ, comma means the coordinate frame is coming. Everything's expressed in body coordinates. And now maybe a little bit you can get a appreciation for why the notation. It seems complicated, but we really need all these letters and slashes and commas. Otherwise you have non-unique representation of the math. I, B, the angular velocity of the body frame with respect to inertial coordinates has special symbols that are taken. They're called P, Q, and R. And I put the body. So we can say that my gyro output is P, Q, and R. This is the sensor, so we can also say these are sensor, rate sensor outputs. So how do I manipulate those rate sensor outputs to get this? First step is to manipulate it to get the rate vector, omega BV in Euler coordinates. And the second one is to manipulate it to get the angles, which is just the integration of this rate vector. That's what we're going to do pretty much this week. The process will break down when? The process that I'm talking about will break down when I'm going straight up or straight down. And so we'll have to introduce quaternions. Which maybe we'll do on Wednesday or so, and then you can do the quiz after that. In this case, if we have the rate sensor outputs in my instrumentation package, I just need this matrix to give me my Euler rates. And once I've got my Euler rates, I integrate them and I show them to the pilot. And I'm done with this week's work, almost. Okay? But here's the problem. This Euler axis, C Euler, has non-orthogonal vectors. So it's a function of IB, J2, and KB. And these are non-orthogonal. Now we can see that by looking at the picture that we've been using all along. IB, of course, is this vector over here on the diagram. J2 is in the horizontal plane, so they're perpendicular. I2 is perpendicular because J2 has to be in the horizontal plane, so it's always going to be perpendicular to IB. But look at KV. KV, that defines heading angle rate. Do you see it's an obtuse angle? Whenever theta exists, there's an obtuse angle between IB and KV. You see that? That means that projections won't work. You have to be going into a orthogonal frame. So, this is going to give us a problem, this is a problem. If we find CB Euler, we will go into an IJK frame. This V axis is going to be a function of IB, JB, KB, if you remember your quiz from last Friday. This one down here is a function of IB, J2, and KB. So we can follow our rules for finding this matrix, and then if I knew this matrix, how would I get CB to Euler? How would I get, if I knew this matrix, how would I get this one? Not transpose. Transpose will not work because I'm going into a non-orthogonal frame. But what will work? Inverse will work. Inverse always works. So I use my rules to define going into the dextral set. Then I invert this and get the matrix that I'm looking for. We're going into this frame. So the first rule is to find a common vector. All right, so a common vector in this case is going to be IB. So we look at IB, and IB is going to be dotted with. So we lay our finger along IB. We lay along our finger along the frame we're going into. And then we what? We draw a diagram. Well, the diagram is shown up on the upper right or left. You can see the diagram. And now we're going to project the old vectors onto the new vector, which we can do since we're going into a dextral set. So our old vectors are IB and J2 and KB. And now we carry out the mathematics of that projection. What is IB dotted with IB? 1. Project the vector on itself, yeah? So that's 1. What is IB projected on J2? Well, now I've got to use my right brain. Let's go over here. Here's IB, right there. I'm going to drop a perpendicular onto J2. Well, J2 is always horizontal. So do you see that IB, since I rotated this vector up, that angle is always, I rotated about J2, so IB has to always be perpendicular to J2 since I rotated about the J2 vector to get it. So the next element is, what's this next element here? 0, yes? 0. The third one is IB projected on KV. Now our right brain is going to get taxed a little bit. So let's go over here. Here's IB, and here's KV. Okay, we rotated about the J2 vector. So IB originally was perpendicular to KV, yes? As I rotated through theta, do you see how if I drop a perpendicular, I'm going to drop on the backside of KV? Does everybody see that? As I rotate up theta, if I rotate this angle, if I drop a perpendicular onto KV, I'm going to be dropping it onto the backside like so. Yes? So what's the projection going to be equal to? Minus the sine, because I'm minus the sine of what? Theta, right? Okay, that takes care of the first row. How do I get the second row? I lay my finger along JB. I lay my finger along JB, so I'm going to have JB dotted. Okay, so let's work this one out. Keep our right brain going. What is IB? What is JB dotted with IB? What's JB dotted with IB? You can't, let's see, my old neurons can't be ahead of you on this one. What's the projection of JB onto IB? Got to be 0. Okay? Got to be 0. How about JB and J2? You with me? Let's locate them. J2 is in this horizontal plane. JB is rotated in this disk. It's just rotated in that disk perpendicular to IB. So do you see if I drop a perpendicular from JB to J2, it's through the cosine of B, right? Is that right? Yes? JB dotted with J2 is cosine phi? Yes? I can see a lot of, okay, if you're not following me, please come see me tomorrow night, okay? All right, now we're going to really tax you. Right brain. Put the women to work here. Women have good right brains. JB, KB. JB, KB. Well, this is a little difficult now. First I want to project onto K3, drop a perpendicular onto K3, and then project that projection onto KB. So if I drop the perpendicular from JB to K3, that's going to be minus the sine of phi. The minus the sine of phi is going to get projected through theta onto K3 projected onto K2 is going to be cosine theta. So this is going to be minus sine phi cosine theta. Minus sine phi cosine of theta.